Hi, welcome to Quick Solutions All India AIATS Test Series JEE Main 2021 Test 5 Code C&D Physics. Let's go to question number 1. Question 1 says 3 rods of material X and 3 rods of material Y are connected as shown. Thermal conductivity of X is K and that of Y is 2K. All the rods are of identical dimensions. The points A and E are maintained at 120 degrees C and 20 degrees C respectively. The temperature of junction C in steady state will be, and this is the arrangement that's been given to us. There are 3 rods of X and 3 rods of Y, and we have also been given the temperatures at A and E, which are 120 degrees C and 20 degrees C respectively. Then we are supposed to find the temperature at junction C in steady state. Well, it's very obvious that the question is from the topic heat transfer by conduction, and let's start solving it now. So since A is at higher temperature compared to E, we can consider that, say, heat current H is flowing in this direction. Now, a very important point here is that this arrangement of the 5 rods. Now, we can see that thermal conductivity of X is K and that of Y is 2K, which means that thermal resistance, let's call it R of X, each rod of material X will be 2 times thermal resistance of each rod of Y. Why? Because we know the expression for thermal resistance is L upon Ka. So that means thermal resistance is inversely proportional to thermal conductivity. So for rod X, the thermal conductivity is K and that for rod Y is 2K. So Rx is going to be 2 times Ry. Now if we look only at this arrangement, we can see that this resistance is equal to this resistance and this resistance is equal to this resistance. That being the case, no heat current will flow through the section CD. Okay, this is also very analogous to a Wheatstone bridge in current electricity. There the quantity that flows is electric current. Here the quantity that flows is heat current. And in case of Wheatstone bridge in electricity, if this resistance upon this resistance equals this resistance upon this resistance, then no current flows through the bridge CD. So that means we can remove part CD, and the arrangement then is simply like this. We have this kind of arrangement effectively. No current is going to flow through CD. So now if this current is H and here the resistance is in the ratio 2:1, so that means the heat current will divide itself in the ratio 1:2. So it means that here the heat current is H by 3 and here it is 2H by 3. And again here also it is H by 3 and here it is 2H by 3 and then again here it is H, and then these are points A and E respectively. A is maintained at 120 degrees C and E is maintained at 20 degrees C. Now we can also use the fact that in general heat current H is the temperature difference. We can call that temperature difference across the ends at delta T divided by the thermal resistance R. So then we have the equation. If I call this point, of course, is B, so it means that H is equal to 120 minus temperature at B, and of course the temperatures are in degrees Celsius, divided by thermal resistance of part AB. So this is, we can call it Rx because it is also made up of X, and also that H by 3 in fact is equal to, so H by 3 for this part, the thermal resistance we can see is 2 times Rx. The temperature difference will be TB minus TE, so that means it is TB minus 20 divided by 2 times Rx. So we have one equation here and other equation here. Let's divide 1 by 2, and if we divide 1 by 2 we get 3 on the left hand side, and on the right hand side we get 120 minus TB divided by TB minus 20, and again there will be 2 in the numerator here. Let's solve it. This implies that 3 TB minus 60 on cross multiplication is 240 minus 2 times TB, or 5 TB is equal to 300, and TB itself is equal to 300 divided by 5, which is 60 degrees C. But we have to find TC. Now another interesting point is that TB minus TC equals TC minus TE, because the heat currents are same in BC and C. The thermal resistances are also equal, so temperature difference will also be equal, and this tells us that TC is simply TB plus TE divided by 2. So now that we have values of TB and TE both, we can easily find the value of TC. So it is 60 plus 20 divided by 2. That means it is 80 by 2, or it is simply 40 degrees C. So we have the temperature of junction C now, which is 40 degrees C. So that means for question 1, option 3 is correct. Let's go to the next question now. Question 2 says, in a new proposed temperature scale, the unit of temperature is Z. In this temperature scale, the ice point is 10 Z and the steam point is 150 Z. The specific heat capacity of water in this new scale in joule per kg per Z is. Well, the question is from the topic thermal properties of matter, and specifically from the topic thermometry. We in fact know the specific heat of water in SI units is, it's 4200 joule per kg per Kelvin. That is specific heat of water in SI units. Now we have here, in fact, the given unit is joule per kg per Z. So we have to convert this per Kelvin into per Z. And for that, we see that the difference of the steam point and the ice point in Kelvin is 100 Kelvin, right? We know that the steam point in degrees Celsius is 100 degrees Celsius and ice point is 0 degrees Celsius. So the difference is 100 degrees Celsius between the two, and a difference of 100 degrees Celsius is same as difference of 100 Kelvin. So 100 Kelvin here is equal to, I'm talking about the temperature difference of 100 Kelvin is equal to temperature difference of 150 Z minus 10 Z, that means 140 Z. So it means that we can put Kelvin interval as 140 by 100 Z interval. So specific heat of water we can write as 4200 joule per kg, and there is Kelvin here, so for Kelvin we can write 140 Z by 100, so 100 will go in the numerator. If we simplify it, it is coming out to be 3000 joule per kg per Z, and which is clearly matching with option 1. So for question 2, option 1 is the correct option. Let's go to the next question now. Question 3 says the temperature of a uniform rod of length L and coefficient of linear expansion alpha is increased by a small amount delta T. The fractional increase in the moment of inertia about its perpendicular bisector is. Okay, we can see that this particular question combines the concept of moment of inertia as well as thermal expansion. Now the expression for moment of inertia of the rod I is ml square by 12 about the perpendicular bisector, and the temperature has been increased and so there is thermal expansion. So from this we can easily get by differentiating or by first taking log on both sides and differentiating and recognizing that mass is going to be constant. We can see that delta I by I, of course for small fractional changes, can be written as 2 times delta L by L, and delta L by L is simply alpha delta T. So that means the expression on the right hand side is 2 alpha delta T, and so we readily get the answer. Pretty simple, isn't it? It is matching with option 2. So option 2 is correct for question 3. Let's now go on to the next question. Question 4 says an ideal gas is taken through a process Pt square is equal to constant. The thermal coefficient of volume expansion of the gas is. Okay, so in this particular question we can use the ideal gas equation and of course the definition of volume expansion of the gas. So first of all, to get the expression for volume expansion of the gas, we know that we can write delta V, small change in volume of the gas, can be written as the coefficient of volume expansion gamma V delta T, and this in fact gives us the fact that gamma is 1 by V dV by dt. Okay, so this is what we are going to use, and of course we will also use the ideal gas equation. Now we see that we are interested in the expression 1 by V dV by dt, and we have been given that Pt square is equal to constant. So we have Pt square is a constant, and let's use Pv is equal to nRT and replace P because we want our expression in terms of V and T. So that means P can be substituted as nRT by V, and if we do that in the first equation, then we have T by V into T square is equal to a constant, and that means we have TQ is equal to some constant K into V. So the given equation basically transforms to this equation, that is TQ is equal to K into V, and let's differentiate both sides with respect to T. Then we get 3T square is equal to K dV by dt, and we can further replace K as TQ by V, and if we do that, it is equal to TQ by V dV by dt, and this gives us the fact that 3 by T is equal to 1 by V dV by dt in this particular question, and which is nothing but gamma, the coefficient of volume expansion. And if you look at the options, it is matching with option 3. So option 3 is correct. Let's now go on to the next question. So here we are with question number 5, which says identify the incorrect statement for an ideal gas. And the first statement is for isochoric process delta V is 0. So in fact, which is true, that isochoric process means the volume is constant, so change in volume will be 0. It's a correct statement. We have to identify the incorrect statement. Option 2 says for adiabatic process delta Q is 0, which is also factually correct. Option 3 says for a cyclic process delta W is 0. Well, in a cyclic process delta W in general is not 0. In fact, it is the area of the PV graph. Say for example, if we have a PV graph like this, let's say like this, then it's a cyclic process, but area of this rectangle in terms of P and V is going to give us the work done, and which in this particular case will not be 0. So statement 3 is an incorrect statement, and so 3 becomes the answer for this question. In fact, we can also look at option 4, which says for an isothermal process delta U is 0. Well, this is also a correct statement. So it's very clear that for question 5, 3 is the correct option, which is an incorrect statement, but we are supposed to find here the incorrect statement, and that's why option 3 is the answer to this question. Let's go to the next question now.